In the previous video, we talked about logical and arithmetic shift instructions. We also did the rotation instructions, rotate right. We did a few examples to show how the data is changed when you shift the bits left and right. In this video, we will talk about arithmetic and logical instructions. Arithmetic, as the name suggests, are the instructions that perform add, subtract, multiply, etc. So we'll start here with arithmetic instructions. And for example, we have the add instructions, or add instruction. We have the subtract instruction. There's multiply and so on. So for example, if I want to add two numbers, I want to add a value to a register, I can perform this addition between two registers. So let's say R1, R1, and R2. This is equivalent to saying that R1 equals to R1 plus R2. And the way I try to remember this instruction is imagine that this is an algebraic equation. The first parameter is on the left side of the equation. So if you replace this with an equal sign, and then you replace the second comma with whatever the operation that you have here. So this is an add, so I just place a plus sign here. So this means add R1 and R2 and store the results back into R1. You can perform an addition with a constant as well. So you can do add R1 and then an immediate value of, for example, 5. This will store, the long notation for this would be like R1, R1, and 5, which means store or add 5 to R1 and then store the results back into R1. The shorthand notation for this is just two parameters. So basically you have R1 comma hashtag 5, which means that you're adding 5 into R1 and then storing it back into R1. And subtract works the same way. So if you have a value or if you have two registers, R1 and R2, it follows the same principle. In this case, this means store the result, or R1 equals R1 minus R2, or subtract R2 from R1 and store the results back into R2. If this is a little bit confusing, you are more than welcome to use different values here. So you can use a third register if you like. So in this case, you have R0 equals to R1 plus R2. And in the second example, R0 is equal to R1 minus R2. Let's do a quick example here. I'm going to remove these instructions and let's move some value into our register. So let's say R0, I'm going to move a 0 into R0. I'm going to move, let's see, for R1, let's move a small number like 4. And then for R2, we'll move, actually, let's make this a bigger one since we're subtracting from it. And then we'll move like 2 into R2. Let's compile and load this to the board. So if I run the code down to the breakpoint, now we'll trace through it. So we'll move 0 to R0, 8 to R1, 2 to R2. Here are the values here, the right-hand side. And now what do I expect? If I'm adding R1 to R2, I'm adding 8 and 2. I will get 12, and then 12 will be stored into R0, and R0, I'm sorry, I will get a 10. 2 plus 8 is 10. I got 10 stored into R0. Our number is right here. A is 10 in hex. And now I'm adding 5 into R1. And R1 contains 8. 8 plus 5 is 13. And 13 in hex is D. Here's my D right here. And finally, I have R1 plus R2. And I'm subtracting 2 from 8, so I get a 6, and I'm storing the results back into R0. Oh, not 6, sorry, because we added 5 to R1. So 13 minus 2 is 11, and 11 in hex is B, and here is the B. Now, there is a variation for these instructions. There are There are modifiers that we can add to those instructions. We will talk about them in a little bit. But let me show you the, now instead of the arithmetic instructions, let me show you the logical instructions. Okay, so logical instructions or logic. So those are instructions that you are probably familiar with in other setups, like in digital logic or binaries and whatnot. So like if you have an AND, there's an instruction that will perform a bitwise AND on the content of two registers and store the results into the third register. There's an OR, or there's an exclusive OR, and there's an OR, there's an exclusive OR, and so on. There's a few. There's a move, there's the test, there's a bunch of other stuff. So let's just do one here. So let's do R0, again R1 and R2, and here we'll do R0, R1 and R2, and this is exclusive OR of R0, R1 and R2, and let's see what we get as the result. Okay. So I'm going to run the code down to our logical instructions. So let's take a look at the content here. Let me move this a little bit this way so we can see. And let's do the display in binary because it will make it easier for us to understand or see the results. So here we have R0. R0 is going to store the results, so we're not really concerned about it. R1 contains 1101, and R2 contains 0010. I'm just looking at the last 4 bits since the most significant remaining bits are all zeros. And if I perform an AND, essentially I'm doing a bitwise ANDing of these bits, right? So 1 and 0, if I'm ANDing this one with this 0, I'm going to get a 0. So this will be flipped to 0. And then if I'm ANDing this 0 with this 1, I'm going to get a 0. And then these two 1s will be ANDed with 0, 0. So I'm going to get a 0, basically. So if I perform this step, here we go. I got a 0 stored into R0. Now, if I'm performing an exclusive OR, as you know, for an exclusive OR, the result is 1 if only one of the bits is 0. So comparing the first bit from R1 and the first bit from R2, we see there's only 1. So this first bit of R0 will be 1. And the same thing goes for the remaining 3 bits. So I'm going to get 1, 1, 1, 1. So if I step through it, I got my 1, 1, 1, 1. And then I'm sorry, we did an OR. We did an OR that would work, and actually we'll probably get the same result if you do an exclusive OR. So we got our 1, 1, 1, 1 here as well. So let me backtrack a little bit and run it to the breakpoint and just go over the OR. Obviously, 1 or 0, that will be a 1. 0 or 1, that will be a 1, and then 1 or 0 will be a 1, and 1 or 0 will be a 1. So both of these instructions will, in this case, will result in the same value, and that will be 1, 1, 1, 1 for and stored into R0. Now, let me show you one more instruction that can be helpful. There's another type of instruction that's called the comparison instructions. So here we'll just write comparison or compare. And those are instructions like CMP, which is a compare. There is the, what else? There's CMN, and there is one more, I think, BIC. Anyway, so the point of this is that you can compare two registers and then update the status of the CPSR. And let's take an example and we'll backtrack and see where this is helpful. So let's say this instruction takes 2 parameters, okay? So let's say I'm comparing R1 to R2. So let me run this code and then I'll show you the outcome here. Okay, here we go. Run the code. Down. We run these. And now R1 contains our value 1101, and then R2 contains 0, 10. So R2 is essentially 2. and R1 is 13. So if I move this, if I step through this instruction, nothing really has changed here. Even the CPSR, what's going on? What happened is that the compare instruction essentially under the hood, it performed a subtract and it discarded the results. And since R1 actually is more than R2, we did not end up with a negative value. So we'll talk about how we do the modifiers in the next video. But maybe I just wanted to tell you that if you actually do a comparison, the program will perform one of these arithmetic instructions under the hood, and then or the logical instructions, and then it will discard the results. You don't need to store the results. You're only interested in the comparison of the two values. So, for example, if I were to ask you, for instance, which number is bigger, 5 or 7, it's obvious to you that 7 is bigger. But if you want to do this mathematically, one way to do it is to subtract these two numbers, right? And if you get, for example, if you do 5 minus 7, you'll end up with -2. So you know that 5 is two numbers lower than 7. So 7 actually is the bigger number, right? And so the way if you get, for example, if you're subtracting two numbers like 7 minus 7, you will end up with a 0. So you know that these two numbers are equal. It will probably make more sense if you're using x and y. So if you're subtracting y from x and you get a 0, then this is an algebraic equation that means x is actually equal to y. So one way to compare two numbers is actually to subtract them and then look at the result, right? If you get a negative result, in this case, then y is bigger than x. If you get a positive result, then x is bigger than y. And if you get a 0, that means x is equal to y. And when you do comparison in assembly, or when you do this instruction specifically, it will perform the subtract under the hood, but it does not need to save the value anywhere. Rather, it will just keep track of what the result was. So logically, if you actually flip those two registers, we should see some things happening in the status registers. This is the CPSR, which is the current program status register. If we compile and run, let me pause the video until it downloads. Okay, go here. Okay, so if I run this program now, I come down to these instructions, which we did a minute ago. And now if I execute this comparison instruction, nothing in the registers here will change, but the CPSR values will change. So just keep an eye on this register. Ah, okay, something has changed here. So essentially, like I said, this instruction is performing a subtract, and it's realizing that actually R2 is, or R1 is bigger than R2. So when it subtracts R1 from R2, it's getting a negative value. That value is not stored anywhere in your register set, but the result has been indicated using some sort of flags. Those bits represent different value or different status in your program. And one of these flags is a negative. There's a one for overflow. There's one for the carry, and so on. So in the next video, we'll talk about how to make use of those flags to kind of control the flow of the code or the program in assembly. Thank you for watching.